This lesson is about object-oriented programming. The concept of an object is omnipresent in programming languages today. It's a simple idea, a data abstraction that contains both the value and the operations together. And the first major system that made this idea popular, that showed how you could build a complete programming system based on this idea, was Simula 67. And later came Smalltalk and C++ in the 70s, 1980, and after that almost all modern languages are influenced by these languages and have incorporated ideas from object-oriented programming. Unfortunately, what this means is that object-oriented programming has, to a large degree, become a buzzword. A buzzword which means it doesn't, in the literature that you see, in advertisements and so on, it doesn't always have a precise technical meaning. It's used just to give kind of an aura of the system being good and advanced. And in modern languages, there are many variations of these ideas of object-oriented programming, but they're not always correct. So, for example, many so-called object-oriented languages do not provide proper encapsulation. C++ allows you to look inside of the representations of data abstractions, which is not allowed normally in a data abstraction. And JavaScript also has very leaky data abstractions where using simple tricks you can bring out the internals of a data abstraction. Another problem is that many languages do not properly support inheritance. They were designed before that it was understood that you have certain kinds of principles that you need to do correct programming with inheritance. A principle that we will see called the substitution principle. And a language like C++ does not have a good support for this. It was basically just designed before that this principle was well understood. Another point is that object-oriented programming is not always the right paradigm. People sometimes tend to think object-oriented programming is kind of a panacea, and if a language is not object-oriented, then it's not good, it's not modern, it's not advanced. But that's not true. For example, there is a language called Erlang, which is in fact much better for building fault-tolerant systems that are able to survive both software and hardware failures, systems that can be distributed, that have high availability, which means that the chance that the system is working at any instant is very high, is close to 100%. So in this course, we will try to be rigorous and focus on the main principles of object-oriented programming. So we're not going to let ourselves be influenced by the hype. We're going to look at the actual principles. And there are three main principles that object-oriented programming provides for structuring programs. The first and most important principle is the data abstraction idea. So we've already had a lesson on that, providing guarantees that part of the system is working correctly, reducing complexity, letting building systems in big teams, and so on. So this is the basic, most important contribution of object-oriented programming, that we build systems with data abstractions. It's hard to imagine in the 1970s that this was controversial, but in fact it was, and in those days most systems did not provide many abstraction concepts. The second principle is called polymorphism. This one is very important next to data abstraction because it allows you to compartmentalize responsibility. That means if you make a design decision in a large system, you should not have to modify many different parts to implement this design decision. You should have to modify only a small, isolated part. And if you change your design decision, you should only have to change this part. So the notion of compartmentalizing responsibility is very important, and polymorphism supports this. So we're going to look at that. And the third principle is called inheritance. And this principle is important to avoid redundancy. So the same code, the same pieces of program that occur in many places, this is very bad, because if you want to fix errors, you have to fix all of them. Somehow they have to remain synchronized, and this is very difficult. And maybe they're slightly different, and then things become even more difficult. So in inheritance, we can build data abstractions incrementally, and in that way we can avoid the kinds of redundancy that otherwise would happen. So these three principles are, from the purposes of this course, are the main principles of object-oriented programming, and a system that calls itself object-oriented must provide all three. A final point is the notion of abstract data types. Now, since object, the word object in object-oriented programming makes you think that objects are the most important thing, in fact, that's not true at all. In fact, what the most important thing is data abstraction. And languages, modern advanced languages, will be mixing the two concepts because they provide different kinds of properties and abilities, and you need both. So, for example, a Java object is actually a mixture of a pure object and a pure abstract data type. And this mixture is very important. It was not a mistake. It's an intentional design decision, and it's important. So we can say that an advanced object-oriented language today is actually a data abstraction languages. And in fact, we should call them data abstraction languages and not object-oriented languages.